One thing we commonly ignored in our first study of physics when we were studying algebra-based physics is the drag force. The drag force, a common example is air resistance, occurs whenever there's relative motion between an object and a fluid. In this case, a fluid is anything that flows. So air is a very common example of a fluid, but also water is another example that we'll study. The direction of the drag force is opposite the direction of the motion of your object, or we could say that the direction is the same as the direction of the fluid flow relative to your object. An example of this is if you stick your hand out of a moving car window. You will feel the force of the air pushing on your hand, and that force will push your hand in the opposite direction the car is moving, so the opposite direction your hand is moving since you're inside the car, which also happens to be the same as the direction that the air is moving relative to your hand. One of the reasons that we ignore the drag force when we are first studying physics is because it can get complicated very quickly. So for AP Physics, we're only going to deal with objects that are blunt, which means that they're not thin, so they're not slender, they're blunt objects, and their relative motion is fast, so that the air becomes turbulent behind the object. You can see an example of that on the right here, where there's an airplane which moves very fast through the air, and that creates kind of circles in the air behind the object. And this happens when anything is moving relatively fast. We just typically can't see it because it's usually air. So when we're actually thinking about determining the drag force, it commonly depends upon either an object's velocity or the velocity squared. There are other relationships that could happen, but these are the two most common. This should make some sense. If you think about probably our most common example of air resistance when you're sticking your hand out the window of a moving car, if the car is moving faster, then you feel a bigger force on your hand than if it's moving slower. So a common equation is that drag force or the resistive force, F sub r, is negative kV, where k is a constant, or that the magnitude of that resistive force could be some constant times velocity squared. So thinking about these relationships, what happens to the magnitude of the drag force as the velocity increases? If you answered that the magnitude also increases, you would be correct. Also, then thinking about what happens to the magnitude of the acceleration of the object as the velocity increases. Well, the acceleration would be kind of negatively affected by this drag force. And so as the drag force gets bigger, the acceleration often gets smaller, especially for objects that are falling in the air. When something is falling, it has the gravitational force pulling it downward and then a drag force pushing it upward. So as that drag force increases and increases, eventually it gets to a point where the drag force has the same magnitude as the gravitational force. When that happens, an object reaches what we call terminal velocity, because if the upward drag force is equal in magnitude to the downward gravitational force, the net force on our object is zero. Once something reaches its terminal velocity, it's no longer accelerating, so it remains at that velocity for the rest of its motion. Now, as we're analyzing drag force, we will often need to use something called the differential equation, which is an equation that contains both the variable and the derivative of that variable. So an example here is that mass times the derivative of velocity. Now we know that that derivative of velocity dv dt is really acceleration. To the left-hand side of my equal sign here is really mass times acceleration, or force, is equal to a constant b times the velocity squared. This is a differential equation because both velocity and the derivative of velocity are in the same equation. We can use differential equations to determine an expression for the velocity of an object as a function of time before it reaches its terminal velocity. So let's say that I want to know how fast something is moving after 1 second. Well, if we ignore drag force, that's a pretty easy calculation because when objects are in free fall, they have a constant acceleration. However, if we're adding drag force in there, that acceleration is not constant, and so we need to rely on solving this differential equation. And solving a differential equation requires two processes, something called separation of variables, and then we'll also have to use our calculus skill of integration. Our next example video will take you through these two processes using a practice free response question.